Just waiting a couple of minutes to
Yeah.
let people look in. All right, I think we have reached plateau. So hello everyone, welcome to today's Polariton chemistry webinar. My name is Stefan van den Wildenberg and I'm a postdoc in Hual Yuanzhu's group at UCSD, and I will be your host for today's seminar. Before introducing today's speaker, I would like to make a few announcements and to remind the mechanism of the webinar series. Remember to subscribe to our Facebook page called Polariton Chemistry Online Community. This Facebook page is not only intended as a platform where you can share updates and announcements about the webinars, but also we want it to be a space for you to share interesting news about our community. Whether you are particularly pumped about your last publication or you want to communicate about the opening of a position in your group, be sure to share it on our Facebook page and to let know the Polariton Chemistry community. If you missed one of the Polariton chemistry webinars and you want to catch up with it, or if you want to rewatch one of our seminars to make sure you didn't miss a detail, remember, we uploaded the webinar series in a YouTube channel. Also be sure to hit the subscribe button and you will be aware of every posted video. Finally, I would like to introduce the mechanism of the webinar. During the talk, attendees are muted. If you have a question during the talk, feel free to click the raise hand button and I will interrupt the speaker at an appropriate time and enable your audio. Also, you can share your comments or ideas using the chat. Please use the Q&A button to type questions that you want to keep for the end of the talk. We will try to address all of these questions at the end of the talk, but if we cannot answer all of them due to the webinar time limit, we will collect your questions and send them to the speaker after the talk. Now, moving on with today's webinar, it's my honor to introduce Professor Gerrit Groenhof from University of Java as today's speaker. Professor Groenhof obtained his PhD from Rijksuniversiteit van Groningen in the Netherlands in the year 2005. His dissertation investigated the light-induced conformational changes in molecular systems, and he then joined the Max Planck Institute for Biophysical Chemistry in Göttingen in the group of Helmut Grubmüller, first as a postdoctoral researcher and then as a research group leader. In Göttingen, Professor Groenhof acquired an expertise in physical chemistry and spectroscopy of biomolecules, and he also participated in the development of the GROMACS chemical simulation software. In 2012, Professor Groenhof left Germany to found the computational biomolecular chemistry group at Jyväskylä in Finland, where he greatly contributed to the understanding of photochemical reactions in complex biomolecular systems, notably using QMMM methods. In 2017, he started investigating the spectroscopy and dynamics of molecules strongly coupled to surface plasmon polaritons, and equipped with his solid expertise of QMMM, he started developing the multi-scale polariton dynamic simulation he's going to present today. So today, Professor Groenhof will give a talk entitled Multiscale Computer Simulations of Molecular Polaritons. Everyone, please join me to give a warm welcome to Professor Gerrit Groenhof. So Professor, you may now share your screen.
Yes, thank you, Stefan, for this nice introduction. And thanks, Bai and Joel, for the kind invitation to this webinar series, which I have been following with a lot of interest. And it has been very nice the way to actually compensate for the restrictions imposed by the pandemic. And it has been a very nice series, at least until now. Good, as Stefan mentioned. Oh, is there something?
No.
Okay, good. Yeah, so I'm in Jyväskylä, and there's a picture of where I'm working. And actually, at the moment, I'm even presenting from the building over there. It's not always like this. It's not always covered in snow. We also have summer here up in the north. And for example, a year ago, that was on a Wednesday. For now, actually, snow has been predicted. So on the way home, I might get some snow. Good. So what I'm going to present today is the work mostly done by Ilya and Ruth. On the development and application of a computer simulation technique with which we think we can try to understand what happens when molecules are strongly coupled to confined light. And this is a collaboration, an ongoing collaboration between Johannes' group, Johannes Weiss's group, Claudia Clement, and locally I work a lot together with Jussi Tappari, who performs experiment on strongly coupled systems. Oh. All right, can everybody see my slide? There is no funny colors in the color boxes in the screen.
Everything looks good for now.
Okay, good. Okay, that happened the last time I presented. All right. Now, what is the motivation for this? So why are we interested? Why is my group interested in performing such simulations of polaritons? And the reason for that is what have been heard many times now, and it has convinced a lot of theoretical chemists to move in this field, is that changes in chemistry have been reported when you put molecules in an optical cavity. Reactivity in the excited state was reported first. That was a paper by Hutchison, which I actually forgot to include here in 2012 in Ankavante, where they showed that the spiral-Piran ring opening was modified by the cavity. And since then, there have been many more examples of chemistry being changed when the molecules are inside an optical cavity. And this then leads to the question, or a very promising question if the answer is yes, is this a new paradigm for catalysis? Can we use strongly coupled systems to change the chemistry and control this? And in order to do so, well, first of all, to answer that question, I think we need to have a much better understanding of what's going on in these experiments. We need theory, we need models. And second of all, if we want to ever use a cavity in a systematic way to change the chemistry of a system, we would also need to be able to predict what's going to happen, and this way systematically design new cavity systems that can act as catalysts. Now, in order to understand the chemical changes, the model must contain sufficient accuracy or chemical accuracy to describe a chemical reaction. And that means that the only modeling that we have available for that is quantum chemistry based, where we're using a quantum chemical description or quantum mechanical description for the electrons of the system, and thereby basically allow for reactivity or photoreactivity. Because experiments in optical cavities are typically performed not on gas phase molecules, but on molecules in a condensed phase environment, where there is either a polymer or another solvent surrounding the molecules which are undergoing chemical reactions, we also need to account, and we want to account for that. And the way we account for that is that we're using a so-called QMMM hybrid model. And that QMM hybrid model, which was introduced by Warshall and Levitt, that got them the Nobel Prize, basically treats only that part of the system where the chemistry matters, where bonds are formed or photochemical excitations happen, so where the electronic degrees of freedom are crucial. It will only treat that part by quantum mechanics, by an appropriate level of quantum mechanics, while the rest of the system can simply be modeled by a so-called molecular mechanics force field, which is a computationally cheap set of functions corresponding to simple intuitive chemical concepts such as bond angles, etc., with which very large systems can be treated. So with our software, millions of atoms is not a problem. So this way we can account for example, a polymer matrix or a solvent environment. Now, because all the experiments that have reported changes to the chemistry have always been experiments in which there was very many molecules coupled to the cavity. It was not one molecule, but very many. We also want to take into account these collective effects. We not just want to model a single molecule in a cavity, but we want to model what happens when you put a very large number of molecules in the cavity. And in order to do that, in order to do this kind of QMMM calculations that are here, in order to perform those, for a very large number of molecules, we have to resort to parallel computing. And this is a picture of a new parallel computer which is being installed at the moment in Finland, which is almost reaching exascale, so almost exaflops floating point operations per second. And that kind of hardware we can harness in this work to simulate a very large and realistic number of molecules. Now, in order to model the cavity, we're using, well, probably the most basic and simple model. We're using the Rabi model, which basically describes the interaction between the molecules in the confined light mode as follows. We have a term for the molecular excitations, a term for the cavity excitations, and can of course be many cavity modes, and then the interaction between the two of them, which is simply given by the dipolar interaction of the molecule, of the transition dipole moment of molecules with the cavity field. The dispersion of the cavity is something we also wish to include, because optical cavities in which chemical changes have been reported were always of the Fabry-Perot type, meaning that it is not a single mode that is coupled to the molecules, but there is a whole range of modes because these cavities support this dispersion of the incoming light. And finally, we also would wish to model the decay, because that is also something that in ideal cavities there would not be a decay, but of course then you can't get the photon in. In experimentally, in all the cases where experimentally changes were observed, these were low Q cavities, meaning the photon lifetime is relatively short. So all these aspects we now wish to put together into a model with which we can then simulate what would happen to the molecules if you put them together inside an optical cavity, supporting both dispersion and photon decay. Okay, it doesn't work. All right, so the Rabi model for a single cavity depends on the coupling between the molecules and the cavity mode, and that is given, as I mentioned before, I didn't mention that yet, but that is given by the overlap between the transition dipole moment and the field of the cavity given by this expression, which can be where you can control the strength of the interaction by modifying the cavity volume, which in practice is of course very difficult, but that is one way to control it in the simulations. Now, if we want to work with this on a computer, we first need to introduce a discrete basis in which we can write the matrix form, which is Hamiltonian, diagonalize it, and perform whatever we need to perform in order to simulate something. So the basis that we use for the light matter hybrid states, there we have to introduce some severe approximation. And the first approximation is that we only treat the ground and the electronic excited states of our molecules. This is also a pragmatic, so this may not always be valid, so you have to check in advance carefully for your molecules. But it is a very pragmatic approximation in the sense that it is already very hard to use quantum chemistry to model the first excited state, the singlet excited state of the molecule. Well, if you want to go beyond singlet excited state and go to the higher excited states, it's almost like it doesn't really matter. So models, quantum chemistry models, except of course multi-configurational and multi-reference methods, have a hard time describing excited states. So it's also pragmatic to reduce to restrict ourselves to only the first excited state manifold. The second approximation is that in principle, this is unbound with the number of excitations, but we have to truncate this necessarily to a number of excitations. If we do that, then our basis in which we now want to expand this Hamiltonian, in which we write down this Hamiltonian, is a very simple product basis of Fock states of the cavity mode and of molecular excitations. So mind you, this is for a single cavity mode. Now what we have is a zero excitation subspace, in which case no molecule is excited, they're all in the ground state, and there is no fault in the cavity. One excitation in which one of the molecules, each basis element has one of these many molecules excited, or all the molecules in the ground state and a cavity excited. Two excitations, now yeah, you get the idea. So now two of these molecules are excited, and in three excitations, three molecules are excited, or there is up to 3 photons in the cavity. So the total number of excitations in this situation is 3. What is important to realize is that on a computer, each of these states can be modeled. We can model the ground state of a molecule, we can model the excited state of a molecule, for excitation and so on. Now the problem with this is that the size of the basis increases dramatically painfully with the number of molecules, and the number of excitations. So here is a log plot of the number of states, and that blows up in your face dramatically. 10 to the power 29 is a very unfriendly number. So we have to stick to the axis of this plot in order to do something on a computer, and that is of course a limitation. But nevertheless, importantly, we now have the full Rabi model, which we can later on compare to approximations of the full Rabi model. And then there we have an overlap between numbers of molecules and numbers of excitations. So we can use this to validate things. Now, within the matrix representation with that basis that I just introduced, the matrix takes this form. You have diagonal blocks corresponding to no excitations, 1 excitation, 2 excitations, 3 excitations, with a couple of off-diagonal terms coupling these blocks via the counter-rotating terms, which create both an excitation in the molecule and an excitation of the cavity mode. The matrix elements of this Hamiltonian are shown here. So there's a lot of terms, and I've been very creative copy pasting these things. So you have the ground state here, which is just basically the energy of all the molecules in the ground state. Then you have the first element of the one excitation manifold, which has the first molecule in the excited state. So in this case, you want to have the expectation value of the energy where the one molecule is excited, the second molecule is not excited, and so on. Then for this element, it's the same, but now the second molecule is excited, and so forth and so on. The last element of this one photon excitation block for a single mode cavity contains then the cavity photon excited and all the molecules in the ground state again. And the coupling between these terms within this block is given by the transition dipole moment expectation value multiplied by the cavity field. You have to take into account that there is a square root of the number of photons there, but all of that can be done. So all of these elements can be computed, pre-computed, put into the matrix, and then you can proceed. And what is important to realize is at this point is that all these situations, all these energies can be computed with the QMM model. So for example, for the ground state, what you have to give me, if I want to have a lot of molecules, for each molecules, you give me the coordinates of all the atoms. For each molecules, I can calculate either the ground state or the excited state, depending on which element we're talking about, and get a number. Yeah, for the excited state, for the first molecule in the excited state manifold, in one photon manifold, I just have to calculate the potential energy of the molecule one in the excited state, molecule 2 in the ground state, and all the other molecules in the ground state, and so forth. So I have a very easy way to actually I can access all these values, all these numbers, plug them into the table. I have also easy access to these off-diagonal terms because that always calls for the transition dipole moment, which is also a computable quantity that you can actually compute in these QMM setups. And this way, by calculating the QMM energy and gradients, you can actually fill up this whole matrix. And I think there's a question. Maybe now's a moment before I go to the next slide. Yeah.
There is a question. Gerrit, you can talk.
Yes, perhaps I missed it, but there should be a source of excitation also in somewhere in the Hamiltonian.
Well, in a way, a source of excitation are these counter-rotating terms, but the way it works is that we basically calculate what we put the photon there. So we do not do a time-dependent excitation. We start with specific initial state that can be with a photon, can also be without a photon. Is that clear?
If you have a decay, then you should also have an excitation, no?
Yes, but we can start with the initial state already excited. So we can choose our initial conditions or initial state such that there is a photon in the system, or 2 photons or 3 photons. The decay part I'll come to later. We treat in a very ad hoc fashion. So we don't, this is a Hermitian matrix. There is no decay terms in this matrix, the way we do it. I'll come to that later in a couple of slides, how we treat it, okay. But it is not via an anti-Hermitian. Okay, good. And I saw there was another hand raised.
That's right. Peng Fei, you are online.
Hey, Gerrit, maybe I missed it. Have you considered intermolecular interactions? Those, electrostatic intermolecular interactions?
Yes. So you're talking now, sorry, you're referring to the fact that the molecules, when they're close together, they can also have Coulomb interactions with each other.
That's right.
Yes, no, that is something we can switch on or off. So we can either switch it on in a like an embedded fashion. So we can add them a posteriori after the calculations are done. That is expensive. We can also, if we're only interested in the excitonic coupling, so like the J coupling is often called, those terms we can actually include in the off-diagonal terms of these blocks here. And we can use an exciton model to calculate those. We have not done that, but that is something that we have a line of opening in the code where this can be included if you would really want to look at very high concentrations where excitonic coupling should be included. Or if we want to compare the effect of strong coupling to the cavity mode to the excitonic interactions.
I see. Thank you.
Yes. There was again something in the corner, even though I think Stefan, that is your task, right?
Yeah, that's okay.
Okay, so
Henrik, you may talk.
Yes, hi. So you have linear expansions of the wave function here. You hear me?
Yes.
Okay.
Correct.
So I was just wondering if you ensure size extensivity.
I think here we have size extensivity because we don't make excitations between
products, right? So do you include all the necessary products in the expansion so you can represent the wave function as a product?
Yes. So the question is the basis complete?
No, but you don't need to be complete. It could just take a few configurations, but you ensure that you get a product wave function, an extensive wave function.
No, we get the linear combination wave. We get a linear combination wave function. So the eigenfunctions of this Hamiltonian are linear combinations of these basis functions.
Yeah, exactly.
I think
but
maybe I have not
typically
understood
not
the
size
question.
extensive, right? So
Okay, but that is something to check. I mean, we can simply double the number of molecules and see if that leads to if that is not the same as twice the energy. Okay, something to keep in mind. I'll make a mental note. It is recorded, right? So I can check that later. Okay, sure. So sorry, I cannot answer the question. I don't know. I think yes, but I'm not. I just think it. I don't know it. Okay. There's more questions.
Yeah, there is perhaps one last question for this slide. For now, you're on.
Hello, I just want to make a quick comment on the size extensivity. So basically, this is from what I understand is like the configuration interaction wave function. So CI in general,
Yes.
well, it is size extensive, but truncated CI is not. So so I don't think if you truncate your expansion, your wave function is size extensive, but I don't know why it is important because you can still use it in computational calculations.
Yes, if you don't want to compare numbers, but if you don't want to compare what happens when you put two cavities together, for example. Yeah, I actually don't know. I mean, within the basis that we use, of course, it is a complete expansion, like all the states are incorporated. So at the moment, I'm confused myself now if this is a problem or not, but this is something I'm going to think about. But I also agree with you that once you have set up a system and you do this, then it doesn't really matter because you're not going to change the size of your system. The problems will only appear if it is not size consistent, if you compare, say, 100 molecules to 1,000 molecules, then it could be an issue, which is something that I'm not certain of now. I'm sorry for that.
Yeah, true.
Mm-hmm. Okay. All right. So basically, all these elements are easily accessible with the QMMM model. You can compute all these quantities, sum them all up and plug them into the matrix, then proceed to diagonalize the matrix, so you get this linear combination of these basis states with the expansion coefficients beta and many betas. And from that, we then derive the forces that act on the molecules. So for example, if we're in polaritonic state K, then we can easily derive on all the atoms in all the molecules, what are the forces if the molecule exists in that polaritonic state. We can perform molecular dynamics, and along with the molecular dynamics to compute the trajectory of all the molecules in the system, we can also keep track of population transfers. Because in general, when there is many molecules, there are many states, and there is population transfer between all of them. And for that, we're using methods such as surface hopping, or we can also do an Ehrenfest dynamics approach. In both of these approaches, we propagate the wave function along with the classical trajectory, like this. So we write it as a linear combination, time-dependent linear combination of these polaritonic eigenstates. Right. Now, an example is this system where we have a molecule, which is abbreviated to the acronym HPQ, which undergoes ultra-fast proton transfer, intramolecular proton transfer. When you excite this molecule in the UV, so 308 is the absorption maximum, then very quickly you have a proton transfer from this oxygen over here to the nitrogen over there, and that is accompanied by a huge redshift. So what you get is you get absorption in the UV, emission in the red. And in order to be able to put this in an optical cavity, we first need to figure out, do we have sufficient accuracy in our QMM model to model this process? And for that, we tried out a number of things. And what worked out the best for us was a Cambridge-Relip DFT, time dependent, using a moderate basis set size and a Chromos 96 force field. And what you can see here is the molecule embedded in the solvent, which is in this case cyclohexane. And I leave that away, and we're going to then simulate this. So we simulate in the ground state, and at a certain point, we make an instantaneous resonant excitation. Of course, experimentally, you can't do it, but in a computer, you can do it. So what happens is that at 100 femtosecond, I will excite the molecule. Now it just wiggles around, it's excited, and you see indeed very quickly there is a proton transfer. Now what we want to do next is to put this molecule in the cavity, and there to test an idea that has been proposed many years ago by Johannes Weiss's group, by Javier Calego in a paper in Nature Com. They proposed that one way to modify a chemical reaction by forming a polariton is that the lower polariton, so this would be the excited state surface, it's a profile. What happens is you excite the molecule to the excited state surface. Then on this excited state surface, along this reaction coordinate that includes proton transfer, along the reaction coordinate, the energy goes down until you reach this point. And that is the minimum in the excited state from where only emissive decay back to the ground state is possible. So that is just an interpolation between the reactant and the product. Now, if you form a polariton by coupling this part, by choosing a cavity resonance that matches the absorption, you create a new minimum. And zooming in, you can see that there is a higher barrier in the polaritonic state than in the ground state. So this should slow down that ultra-fast reaction. So the prediction here is if you put this molecule in an optical cavity, then we anticipate that the reaction should be slowed down. To see if that is the case, we take 4 of these molecules, just 4. We make a very strong cavity field, so that is ridiculously strong. The cavity is on resonance with the molecular excitation. We take up to 64 excitations into account, and the reason for that is that when you put the molecules in the cavity like that, there is a Rabi splitting in the order of almost 600 millieV, and that is approaching the ultra-strong coupling limit. But what actually happens when you put this in the cavity and you look at the ground state, then actually the ground state wave function is mostly, so there is hardly any mixing in of multi-photon states where the cavity modes are excited in the ground state. So you don't need it for that. Also in terms of the energy, this ground state in this ultra-strong coupling limit is only moderately affected by the strong coupling. All right, so this is the Rabi splitting. And with this system, if we now do the simulation with these 4 molecules, what you see is going to be very boring, namely nothing will happen. So your molecules all stay nicely in the reactant state due to the strong coupling with the cavity. So it kind of works. All right, but note that we need to take into account a very strong cavity field here. Now, what we would like to do is to reduce the cavity field to more moderate electrical fields and increase the number of molecules. But in this quantum Rabi model, there is really no way. So we have to make additional approximations. And the first approximation we make, like many others, is to assume that we can forget about these counter-rotating terms, which is valid if the cavity is on resonance, is close to the excitation energy of your molecules. In that case, with the counter-rotating term 0, you lose these couplings between the blocks, and then it just reduces to the Jaynes-Davis-Cummings models, where you only have to consider the exchange of an excitation from the cavity mode into the molecules and vice versa, meaning that the excitation number is now conserved. And if we furthermore assume that we only have to consider the single photon manifold, which you typically get if you use weak driving, low intensity fields, in that sense, things become even more simple. Now, if we only focus on this, one photon excitation part of the Hamiltonian, then this Hamiltonian, if you don't incorporate the J coupling between the molecules, has a form of an arrowhead. And within this arrowhead matrix, the matrix elements are again obtained as before. So we can simply, if you give me the configurations of all our molecules, I can calculate very quickly what's the excited state potential energy, what's the potential energy, what is the transition dipole moment. So again, I have all the tools to fill up that matrix, diagonalize it to get the polaritonic eigenstates. These are the Davis-Cummings eigenstates. Do the same trick again to get the Hamiltonian forces, and then propagate this polaritonic wave function along with the trajectories to decide to take into account the population transfers between the states. Now with that model, this model has the nice property that it is very simple to parallelize the model. Now the way we have done this is extremely naive. We just take a large number of cores on a supercomputer, and we let each group of cores or each core compute the excitation energy, the ground state energy, the ground state potential, the excited state potential energy, and the transition dipole moments. And all these, and each of them for a single molecule. So if we have n molecules, we simply take n nodes. The n nodes communicate then these energies and the transition dipole moments to a central node. That builds the matrix, diagonalizes the matrix, sends back the eigenvectors, and each node simply performs the molecular dynamic step for that molecule. So this is very trivial, and you can easily do something like, well, as to test this, we put 4,000 rhodamine dyes in an optical cavity, which was in the order of, at least I cannot see myself the numbers anymore, but a lot of QM and a lot of NM atoms on a lot of CPUs. So the nice thing about the Davis-Cummings model is this linear scaling. in contrast to the full Rabi model. So now we can play the game of varying the number of molecules and see how that affects things. And now if the things are not size consistent, yeah, then we probably have a problem here in the comparisons, but that is something I'm going to convince myself of later on. Yeah, so we can address the question, should you simply increase the cavity volume, decrease the cavity volume to increase the cavity field, or should you increase the number of molecules? Because the Rabi splitting is proportional to the square root of the number of molecules divided by the cavity field, cavity volume. Now, you can, of course, okay, here are the polaritonic eigenstates again. So what has been often done is you take a single molecule and you put it in a cavity with a very strong cavity field. But experimentally, most of the time at least, people put a lot of molecules in a cavity, have a very moderate cavity field strength, because in a Fabry-Perot cavity, you don't have so much options to actually increase that field. So this is two different ways of getting the same Rabi split. And my question is, does it matter? And it does matter, and I'll show you now why. So here are the polaritonic eigenstates again. Mind these coefficients. Now there was supposed to happen something, yes. Now if I look at the forces that act on our atoms, so there is a force on an atom A, which is part of molecule J, then it's given by the expectation value of the derivative of the Hamiltonian element. It is this expression. I mean, I hope it is correct. I think it is correct. Don't worry about where it comes from, but the only thing you need to consider now is, want to talk about now, is that the forces are proportional to the betas, which is the expansion coefficients of each of these basis states in this polaritonic eigenstate, the alphas, and the field strength of the cavity. Now, if you're reaching strong coupling with a single molecule, then beta is a half, but the field needs to be very strong. If you reach strong coupling with many molecules, then these betas get very small, and blue can also be very small. So the force on the atom, if you do a single molecule in a cavity, will be a lot higher than if you put very many molecules in the same cavity. I'm sorry, in a cavity with a weaker cavity strength. Now to illustrate this, so I'm now going to plot some Hellman-Feynman forces on atoms using molecules with identical configurations. So all the molecules are the same. They are all coupled to a single mode cavity that is exactly on resonance with the molecular excitation. And then I'm going to try to reach the same Rabi splitting using varying the field or the number of molecules. So if I want to bring a single molecule in the strong coupling limit, what I need to do is I need to put a very strong field, in which case, well, the coefficient of the molecular excitation is 50% and the cavity excitation also 50%, and I get this Rabi splitting here. And these are the forces. So you see there is forces acting on atoms, also on the proton. There are strong forces acting on these atoms. Of course, I mean, the numbers only make sense if you kind of have a feel what the thermal forces are. The thermal forces are actually also in this range. So this is not super dramatic, but still there are strong forces acting on the molecule. If you now increase the number of molecules to 4, you can actually halve the cavity field. If you increase it all the way to 64, you can make the cavity field even 8 times smaller. And what you can now see is that this leads to a reduction of the contribution of the molecular excitation to the polariton, and at the same time, you can get away with a much smaller field. So you get the same Rabi splitting, but the forces that act on the atoms are almost absent. And because of this, I don't totally understand why there can actually be changes to the chemistry when you put molecules in the cavity. Because in a single molecule, yes, I can understand, because there are strong forces now acting on my molecule. So if I now excite this, I would expect a different behavior than if I would excite just a single molecule. Just a molecule out of the cavity. But in this situation where the molecule is almost like in the ground state, I don't really see how that changes the chemistry, except that it can retard the reaction by just collectively keeping the excitation smeared out and not letting a single molecule becoming fully excited. But it is just something that I'm just wondering about. But it's nice because now with this linear scaling, 64 is still a very small number, of course, but we can easily go to thousands. Now, the other thing of cavities that we haven't talked about yet is that these cavities support multiple cavity modes. If you vary the incidence angle of the light, you can actually vary the energy of the photon in the cavity. Of course, you're fixed in the X direction because that sets the cavity resonance. But along the Z direction, you have freedom, and it means that in order to fit, for a photon to fit in, it follows this cavity dispersion relationship, where the energy of the photon increases when you increase the K vector, or in other words, you increase the incidence angle at which the light comes into the cavity, according to this relationship. So in reality, there are very many cavity modes according to this relation. The coupling between these cavity modes and the molecules is more or less the same as before, except for the fact that the field strength now also depends on the K vector. And finally, in order to model the light in a real cavity, you also need to take into account the form of the electromagnetic field. And for that, the best form, the form we use is that of a plane wave. So the light modes are now described by these plane waves. This is not convenient because this is an infinite sum. In order to make it finite, what we do is we follow a trick by Michetti and La Rocca already many years ago, where if we have a cavity system like this, the molecules are placed along the z-axis, the mirrors on the x and plus at the plus x and minus x axis, the cavity field is along the y direction, and now along the z dimension we apply periodic boundary conditions, meaning that if you cross here, come back there. And that is important because the periodic boundary conditions now set conditions on this kz. So we quantize kz as follows. These become discrete values. So now we can control the number of light modes or cavity modes that we have to incorporate in our expansion. The Hamiltonian in this setup becomes very simple. It's just a 4-block Hamiltonian shown here, where the molecular block, the diagonal elements of the molecular block contain one of the molecules excited, which is the block index, which is the index in that block, and all the other molecules in the ground state. The cavity block is also diagonal, and on the diagonal we simply have the energy of the cavity mode plus all the molecules in the ground state. The interactions between the two blocks, these two interaction matrices, they are again given by the transition dipole moment of the molecules, which depend on the coordinates of the molecules, times the cavity field corresponding to that light mode, times this term which contains this complex phase factor, and that makes the whole calculation a little bit more awkward and clumsy and expensive, but it is not something we cannot do. So this is, again, we can, using the input from QAnon calculations, we can quickly compile that matrix, analyze it, and then perform the molecular dynamics as we did before. Now, there was a question before about the decay, and I think there I probably have to disappoint people because we do it in a very primitive way. So if we use the Stefix QAnon simulation model, well, as I mentioned before, we propagate the total wave function as a time-dependent linear combination of the polaritonic eigenstates, where the coefficients are time-dependent and can also write as density matrix elements like here. The propagation is done with an unitary propagator within the so-called local diabatic basis. The details can be found in the paper by Granucci, also a quite old paper. Then the decay, as I said, is done probably disappointingly simple. We know that the cavity decay always dominates the molecular decay, at least the metal-clad cavities that are used in most experiments. The cavity lifetime is the inverse cavity dissipation rate, and that is simple as a first-order rate process. So we basically decay this diagonal elements of the density matrix by multiplying this by an exponential term, called this first-order decay process, where the size of the decay or the magnitude of the decay depends on how much photonic modes contribute to that polaritonic state. So if the state is dark, there is no alphas, there are no polaritonic states contributing, photonic modes contributing, then the decay will be 0. But if it's, for example, the lower polariton, we have almost 50% or more photonic, then the system will decay quite rapidly. And then the decay constant is a parameter we set in our MD simulations. All right, so with this multiple cavity mode that allow you to include many molecules in the cavity, including the decay, we now can run some applications, try to shed new light or to shed more insight into polaritonic, into strongly coupled molecule systems in cavities. And one of the things that we looked into at first and are still looking into is the relaxation mechanisms in a realistic cavity. And I put realistic here because, of course, it is still a model with its own approximations. So one the things that we are now interested in is, can we actually calculate mechanisms of relaxation, vibrational scattering, radiative pumping? What is the nature of the dark states? What is the exciton reservoir? Are these the same? Are these different? So these are the questions that we're currently trying to address. And to give a little bit of a flavor, something that we recently published, here we have a situation where we put 256 molecules in a cavity, which is still a small number. I'm aware of the field that we need in order to get strong coupling is still quite high, but we can do it. So we can get these 256 molecules in the cavity. We can excite, we can use a resonant excitation into the upper polariton that you can see here. I muted myself, sorry. Yeah, I'm not muted, no?
No, we can hear you.
Yes. I lost now. Oh yeah, so we resonantly excite into the upper polariton at this K vector. And what we then do is we start the simulation like that. So this is maybe coming back to one of the initial questions, like how do you do the excitation? Well, we just start there. Yeah, we just simply say that steps at time 0, we start in the upper polariton at that K vector, and we perform the dynamics. And what you see is that very rapidly population is transferred from the upper polariton into the dark states, which is this black line. And from the dark states that do not have any K vector, from the dark states you can actually access the bright lower polaritonic states at any K vector. So what we actually see if we calculate the luminescence spectrum of this cavity as a function of time, so it is integrated over all the simulation steps, we actually get luminescence all along the lower polaritonic branch. And the reason for that is, as I said, this two-step decay process. You go from the upper polariton into dark states. There you can survive quite long, but from the dark states, you still have access to the lower polaritonic state, and transitions between the dark states and the lower polaritonic states, they will then lead to emission that you can see here. What is now important, and I got the question also a week ago, to realize is that in these simulations, we significantly overestimated the rate of transfer. And the reason for that we know, and that is as follows. So again, we have population transfer between different polaritonic states, from upper polariton to dark, from dark, between the dark, and also from dark to the lower polariton. And here is again an expression for the polaritonic states. And what is important now is that what drives the population transfer between different states is the so-called non-adiabatic coupling. And the non-adiabatic coupling vector, again, a lot of details here. I immediately go to where I want to go. The size of that coupling vector determines the rate of the transfer. If the coupling vector is too large, the transfer is too fast. Now, what we have here is that the coupling vector depends on the betas, depends on the alphas, the expansion here of the photonic part, and depends on the cavity field strength. Now, with only 256 molecules, as compared to experimentally, where it will be 10,000 molecules, let's say, in a polariton, these numbers are way too high. The contribution of each of the molecules to the polariton is much higher than it would be in the thermodynamic limit. And the same is true for the field. The field we choose is still a lot higher than you would need in a real cavity. And that leads to a significant overestimation of this non-adiabatic coupling vector. So mechanistically, I think things are still quite okay, but we are mixing up now a little bit the rates. And that is something that, in order to get over that and to say something about experimental relaxation rates, maybe we can try to extrapolate. It was a suggestion I got last week, but we haven't tried that yet. But this is something to keep in mind, that yes, we can include many molecules. We can use much smaller cavity fields that would not disrupt a single molecule, but we still pay the price of the approximation. That is, in this case, one of the many prices we pay is that we overestimate this non-adiabatic coupling, which is convenient because in a short simulation, we can see all these transfers. But of course, if you want to compare to an experimental situation, then you have this issue. And I saw there was somebody coming by with a question.
That's correct. Gerrit, you have...
Yes, so I guess I have a really stupid question. So you put a single photon and you start the simulation. Precisely. And then when you have a decay, so that photon decays, and then you have to start the simulation again, or?
Well, we use the Ehrenfest formalism in this simulation. So that means that we no longer have a full excitation present, but it simply decays back to the ground state. And once the ground state is totally populated, then the simulation is over. That is one way of doing it. We can also have implemented in two different ways. The other way is to stochastically lose that photon, and then the simulation is over. But that's a little bit silly because once you have started the simulation, you don't want to have it over immediately. But that is how we treat the loss of the cavity, so that you lose your polaritonic state due to leakage to the cavity mirrors, and that we model by this first order rate process.
So you lose less than a photon through the polaritonic state?
In our work, we use less than a photon. We continuously lose the photon, so we leak out in a continuous fashion.
So what remains in the molecule if you lose a fraction of a photon?
Exactly. So the molecules no longer will be able to undergo any photochemical reaction because the photon is gone. And then, yeah, as you said, you have to do the simulation again. So there's two ways of doing this. One is the Ehrenfest, which has its own problems because Ehrenfest is a mean field approach, or you do it with the surface hopping. And in that case, as you mentioned, we have to repeat the simulation once the cavity has leaked. So what I prefer to do is to a posteriori calculate what is the likelihood that you are still excited at this point of the simulation when something interesting happens.
So we have two other questions. Joel, you may talk.
Hi, Gerrit. I have a question about this part of radiating pumping. So I also used to think that, going from the dark states to the lower polariton is like a vibration-mediated process. But then recently, the more I talk to experimentalists, they describe radiating pumping as a process whereby, the dark states stoke shift to their to the S1 equilibrium geometry, and then there is just a single molecule dipole coupling to the new polariton modes of the molecules that were left in the ensemble. And that's the way, and that's the reason why fluorescence has the same timescales outside and inside of the cavity roughly. But then based on this mechanism of the non-adiabatic coupling vector, if I ramp up the number of molecules in the simulation, I would basically see that the excitations would be trapped in the dark states and never go to the polariton modes, right? Because like all these forces, as you say, they go as 1/n. So then can you, because I'm confused about what people talk about when they say radiative pumping. Like I thought this mechanism of fluorescence into polariton modes.
Yeah, well, welcome to the club, because I also do not understand so well the mechanism of the radiative pumping, because indeed it has been mentioned it is an emission plus re-emission process. So the molecular fluorescence then emits the photon in the cavity directly into the lower polariton.
Yes.
And the argument for that mechanism has always been that the rate at which this happens is the same, more or less the same as the fluorescence rate. But that is not true, because if you look at the rates that are reported for cavity lifetimes versus bare molecule lifetimes, they are the same up to an order of magnitude. So it's not the same. There is a difference.
But then people could say, well, I mean, you have like the photonic environment that gives you some factors of like some changes, right? But then
but it's not so big in a cavity.
But what really puzzles me is the scaling of 1/n, because if it really is true, then you shouldn't see fluorescence from these, you know, situations where you have very many molecules per photon mode.
Well, that's what we have here. So
because I mean, because the formulas that you're showing, as you say, go as 1/n, right? Like the expression.
Well, but don't forget there is also the 1/n. The square root of n is also in here. The energy gap between the darks between the states. But okay, yes, this goes like 1/n. Yeah, 1/n.
Okay, wait. The whole thing in the right-hand side goes as 1/n, or you think that there are scalings that go as order 1?
I think it goes as 1/n, but I'm not 100% sure, because also this energy gap term depends on the square root of n. I haven't had time to wrap my head around that one. I mean, this should be there, but the energy gap between the dark state and the polariton state is proportional to the square root of n as well, right? That is proportional to the Rabi splitting.
Okay.
So there is how the n works in exactly as a square root or as a linear 1/n term, I do not know yet. That should not be too difficult to find out. But the point I tried to make was that if you do the simulations with our model, you will overestimate always the rates, because you cannot approximate the actual number of molecules or the actual cavity field strength. But perhaps with this, we can make extrapolation. So test the extrapolation first in the simulation and then compare this to an experiment. And of course, there, if the size extensivity is a problem, then yeah, we have to think about it a little bit more. But these are just ideas at the moment. But the take-home message is that at too strong cavity fields and too few molecules, you overestimate this non-adiabatic coupling.
Sure. Thank you.
Yeah.
We have two more questions. Small notice for the remaining time now. Felix, you may talk.
Yes, hi. Thanks a lot so far for the talk. Can you give a bit of physical insight on what does physically represent this non-adiabatic coupling vector? Thanks a lot.
Okay, yes. So what it means is that if I now move along an atom A in molecule J, if I just move along the atom, then I actually induce population transfer between state psi L and psi M. So this motion couples two polaritonic states. So that means if I move along it, I transfer population. Is that answering your question?
Yeah, that's good. Thank you.
Okay, and Said, you're on.
Yes, thank you for the very interesting talk. So I have a question related to the fact that you do not include the dissipation in the description. So basically that means, I guess, you also don't include fluctuations, right? And I guess this changes the expression for the coupling, right? When you have a quantized field, because you will have that is basically G times the square root of n plus 1, and the 1 comes from the fluctuations in the vacuum field. So I guess you don't have that.
No, because you said, yeah, go on.
Yeah, and I would think that one is very important, right? Because you have you put in one photon, right? And suddenly you're missing the fluctuations in that number. And I'm wondering if you have an idea of how relevant or irrelevant is what I'm saying, the fact that you don't have fluctuations in your system.
Unfortunately, I cannot answer that now because I don't know what to answer.
Okay.
Sorry. But
okay,
yeah.
Thank you.
Okay, good.
So we have 3 more questions. In the interest of time, do you know if you will have time to wrap up with the presentation? How many slides do you have?
Okay,
Yeah?
then we do questions maybe afterwards. If people can keep them, then we wait until the end of the talk. Or we can always stop. All right. Then one other motivation for including the cavity dispersion is polariton transport. And a couple of years ago, I saw a talk by Tal Swartz where he actually presented very interesting results where he sees motion of the excitation of the polariton in a cavity system and at high temperature. Even though this is, in my opinion, more a diffusion process, because if you go at polaritons in inorganic systems, so quantum dots in inorganic cavities at low temperature, then this is really moving with the group velocity of the dispersion where you excite it. Now, this is something that you can only simulate if you take into account the multiple cavity modes, in my opinion. So this is one thing that we were interested in. So we take again this Rodamine model, and I go through this very quickly. We put it in a solvent, water, maybe not the ideal solution if you want to use a cavity, make a cavity. Then we use QMM, where the fused ring system is described at the quantum level. For the ground state, we use just Hartree-Fock with a very tiny basis set, but it's only about the qualitative features, not about the quantitative features here. For the excited state, we make a configurational interaction. It's truncated to single excitation. So now we have the excited state and the ground state models. We can get the potential energy surfaces and potential energies, and we can get the gradients, and we can get the transition dipole model. In addition, we also modeled a so-called stiff Rodamine model. In that sense, stiff meaning that we place constraints on all the bond lengths using the Links algorithm, because this will give changes to the Stokes shift. And we were actually interested in making a molecule with a very tiny Stokes shift, but I haven't found, because in J aggregate, which is a very common molecule to put in optical cavities, the Stokes shift is tiny, and that makes certain things possible that you cannot get with normal molecules. But we try now to model that at high constraints. What we then have is we have a molecule, the normal molecule has a very broad absorption. There is a heterogeneously broad vertical excitation. We can do the same calculation for the emission. So for our normal molecules, if we perform dynamics, we can get an absorption spectrum and an emission spectrum with a relatively large Stokes shift. If we take the stiff model, then the Stokes shift is very tiny, and also the line widths are very tiny. So this is exactly what we wanted to achieve, to see what's the effect of the Stokes shift, what's the effect of the molecular flexibility when this molecule is part of a polariton. We then plug in 250 of these molecules into a cavity of 50 micron length, and we initiate, and this is the dispersion of the cavity, and we initiate our system by exciting the lower polariton with a certain range of K vectors, so distributed via this Gaussian shown here. And these parameters, they come from a paper by Agranovich and Garstein a couple of years ago. If we then simulate this at 0 Kelvin, that would then imitate this inorganic cavity system at low temperature, then the behavior is pretty well predictable. You simply get that this Gaussian wave packet is moving with the group velocity of the dispersion line there, and it's broadening up. Okay, no surprise. But at 300 Kelvin, so where the molecules have all the thermal motion included, and there can also be transitions between the polaritonic states and the dark states, the things are changing. And what you can see here is the polariton, is the movement of the wave packet in the system at 300 Kelvin. And what you see already now, after a few hundred femtoseconds, is that this is no longer a ballistic transportation, but it is more like a very fast diffusion, still with a rate that is very close to the actual ballistic transport we saw at low temperature. But then what was interesting, if we then simulate the stiff molecule in the cavity, so where we have these constraints placed between the bonds, then the behavior is actually a lot more like the 0 Kelvin case, which puzzled us a lot at first, actually still puzzles us, and also the molecular part. So what I'm plotting here, I didn't explain, is the photonic part of the wave function of the wave packet, and this is the molecular part of the wave packet. But you can see here that if the molecule is stiff, that means it has a very tiny Stokes shift, then the dynamics is much more ballistic than in the case where everything is happy and free to relax. Now okay, here is again the same thing plotted. So you see nice motion as a function of time along through the cavity, also here. But in this case, especially the molecular part just diffuses in a way, and is still present at where we started from. Now, why that is, and this is therefore a lot more resembling the situation that Tal Swartz reported for his system at room temperature than the situation you would have at low temperature in inorganic cavities, where you have ballistic transport with the group velocity of your polaritonic branch. Why is that? Well, this is very fresh. So I just made this slide a few hours ago only. Here we compare again the situation. So for the frozen case, they have very tiny lines of the polariton absorption, and the molecular absorption is just a line because all these molecules are the same and they're frozen. At 300 Kelvin, we have this broad absorption, broad Stokes shift, and the stiff molecule has the narrow absorption and hardly any Stokes shift. So if you now look at the populations of the different states, so these are the modes. This is the molecular contribution. We see that in the frozen case, the wave packet that we started from is actually a little bit more photonic, quite a bit more photonic than molecular, probably explaining why the photonic part is bigger. But at room temperature, what we see is that there is a lot of transitions into molecular states. So we start losing populations from the lower polariton into the dark states. And that, of course, affects the wave packet, the form of the wave packet a lot, because these dark states can go again back into the lower polaritonic state. And for the stiff one, which shows this remarkable behavior, we actually realize that if we take the same starting frame as we take in this situation, and we apply the constraints, this is equilibrated structures from a ground state simulation without constraints. If we now apply the constraints, and of course the molecule gets a small kick, we get to a situation where the absorption energy is suddenly higher. And what you can actually see is that leads to a much larger photonic component. The narrower absorption line width, or the narrower density of dark states, causes also a much slower transition into those dark states. So that is why we have a much more photonic behavior that you would get at low temperature. At least that is our current interpretation of these differences. But still, I think this kind of simulations might help us to understand a little bit better how we can optimize polaritonic transfer, or maybe not. All right, to summarize, so I've now talked about a multi-scale Rabi model, multi-scale Tempest-Cummings model, with which we can actually simulate molecules in cavities. And with that, we would like to address can we reshape the potential energy surface in the excited state by forming a polariton and that way control chemical reactions? And another interesting thing that we're trying to do, what I find interesting, is if I have a reactive molecule here and just normal fluorophores everywhere else, can I get the excitations to move there if I choose the excitation conditions correctly? So these are the kind of problems that we're now looking forward to address. And with that, I would like to thank all of my coworkers. And for the sake of time, I'm not going to read all their names. You can do that yourself. And now a few minutes left for questions, which I hope I can answer because I haven't done very well with that yet so far.
Thank you very much, Professor Groenhof, for your wonderful talk. I'm sure we will have a lot of questions now. So Ariel, you can talk.
Yes, Gary, thank you very much for the talk. I have more of a, can you hear me well? Yeah,
I can hear you well, Ariel. Yes.
I have a technical question. When you were discussing how you do the simulations with non-adiabatic couplings, I think I understood that you are using the Ehrenfest model, or
Correct,
was it surface coupling?
Both we can use, but this the work I presented here was Ehrenfest, yes.
Because you're calculating non-adiabatic coupling vectors, and I was wondering, you know that the situation between the dark states is different here than when you have a conical intersection in an isolated molecule. Here you have really a mishmash of lots of states very close together. And I was wondering if in that case would not be advantageous to simply use directly the arrowhead matrix and remain in the diabatic representation.
Yes. Yes, we have talked, I have thought about that. We have discussed that a lot. In particular at the beginning, when we had a lot of problems with all these what is called trivial hoppings, right? When you as you mentioned, you have a very dense manifold of all crossing states. And our solution was not to switch to a diabatic description, but instead to make the compromise and use this local diabatic description that Granucci introduced. So this way we kind of have, well, maybe not the best of both, maybe even the worst of both worlds, because we still have to diagonalize the matrix. But yeah, you're right. I mean, this is something we have thought about at the very, not at the very beginning, but halfway. And in the end, because this time-dependent propagation of the wave function works for us, and also we can take large time steps, we haven't thought yet about changing it.
All right. Thanks a lot.
Yes.
Okay, Arkajit, you're online.
Hi, Professor. Thanks a lot for the wonderful talk. I have a question about the non-adiabatic coupling vector that you showed, and a lot of people had questions on. Yeah.
Yes, I realize I should have not put it, but go on.
Yeah. So in that part, you are showing this non-adiabatic vector between two polaritonic states.
Precisely.
you said that we are overestimating the non-adiabatic coupling when you have less number of molecules.
Exactly.
And when you have more number of molecules, you also have more number of dark states. So, and all those dark states will crisscross each other also with the lower polariton.
Yes.
And so do you think that because of the increase of density states, it will eventually maybe balance out this?
Wow, yes.
So,
That's a very good point. In fact, because we have recently, not recently, I think 2 years ago, 3 years ago, we have actually made a point that the overlap between the dark state density of states and the lower polaritons determines the rate at which you decay. Now, you're right, because if you would use a Fermi golden rule, like this would be the matrix element of the coupling, and then you would multiply that by the density of states. Of course, there might be a crossover, there should be a crossover there as well. That's interesting. Yes, I'm gonna look into that. Thanks a lot for this suggestion, because this is something that now we only look indeed at the one state, but of course at the same time, the number of dark states which can feed the lower polariton will also increase when you increase the number of molecules.
Okay.
Great, thanks.
Okay, we have another raised hand. Sheila, you have the floor.
Yes, thank you very much for the talk. I was curious, you mentioned that in these calculations you're showing, you do not explicitly include the J coupling between the molecules, but that it is possible to do. But yes, what I was wondering is whether you make any assumptions about the relative orientation of the molecular transition dipole moments to the cavity modes in this model, and whether that has to be the same for all of them, for example, or does it matter?
I got it. Yes, it matters a lot. We don't have to choose it. I mean, the model makes no assumption there, but in the simulation that I've showed, I've always started the simulation with all the dipole moments aligned. We don't have to do it. We also have now done simulations where they are not anymore aligned, so that you get actually some molecules hardly contribute anymore because the dipole moment is not optimally aligned with the cavity field. So it is not a requirement to align them, but in the work that we've published so far, we have always aligned them. Simply because these calculations are expensive. We don't want to kind of waste CPU hours by weekly.
Yeah, I guess that was my follow-up. If that would actually, how much that increases computational cost.
Yes, well, it really depends. I mean, the problem is really to get access to computers. So I mean, to get access to a few hundred cores, no problem. But to get access to a few thousand cores, that is still a bit hard. But that will only improve when more and more equipment gets available.
Thank you very much.
Yes.
Okay, so we also have a couple of questions in the Q&A. Do you want me to read them or?
Yes, because I don't see the Q&A. Ah,
okay.
Here's the Q&A. Okay, yes.
So from Kishan, nice talk, Gerrit. Sorry if you have already mentioned it, but have you considered the scenario in your model where when you excite the lower polariton and bypass the reservoir?
Yes, we have done that. So in a previous paper, I think in 2019, we have looked at what happens when you excite off-resonantly a molecular excited state which is above the polariton manifold. We have checked what happens when you excite the lower polariton, and we have checked what happens when you excite the upper polariton. And what happens there is that, I don't know what you mean by bypassing the reservoir, but yes, you can directly excite the lower polariton. Of course, there is a strong dissipation of the cavity photon because it's a low lifetime. But there, what actually happens is from the lower polariton, you also occupy the dark states. So there is two channels. One is the photon emission, and the other one is transferred to the dark states.
Okay, and we have a question from Bill Barnes. Really nice talk. Question, do you think that the expectation you now have about polariton propagation will be modified when one includes vibrational modes?
No, and the reason why not, Bill, is that we already include the vibrational modes. Okay, we don't have quantized vibrational modes because we're using a classical molecular dynamics model, but in the simulations that I was showing towards the end, where we see this wave packet moving, all the molecules were simply moving around. And they were coupled to a temperature bath at 300 Kelvin. So there was an environment, there is the molecules, everything is vibrating. So all the vibrational modes are accounted for. The only approximation that we make, which may be very severe, is that these vibrational modes aren't quantized. They are just described as classical.
Okay, so I think, so he says thank you. I think we have resolved all our questions for now. If you would allow me to share my screen, I would like to make
yes.
announcements.
Did I stop? Because I still see.
Yeah, I think so. I just need to do this. Okay, so thank you again for your wonderful talk and very interesting. And thank everyone for the attendance and the nice discussion during the talk. So before closing the webinar, let me remind you of the schedule for the next webinars. As you can see, we have a lot of interesting upcoming talks, so be sure to register every week. And next week, we'll have Professor Markus Raschke as the speaker with the talk entitled Tip Enhanced Strong Coupling, Broadband Room Temperature Picocavity QED with Single Emitters. The registration can be made through this link over here, or the link you will find in the reminder email we'll send you later. I hope I will see you all next week, and thank you again.
Yes, thank you. Is it possible to copy from this chat? Because Tao Li suggests